So we've been talking about relational expressions, and now we're going to take a look at evaluating some of these expressions, and we'll talk about some more details as we go. First, let's review the arithmetic or mathematical operators. So as we discussed, the mathematical operators operate on numbers and are part of expressions that evaluate to numbers. So when we have an operator like the addition operator with two operands like 3 and 5, that's going to evaluate to a value, in this case 8. So mathematical operators, arithmetic operators, numbers in, numbers out. And with the mathematical operators, arithmetic operators, there's an order of precedence that we have to be aware of. And it's the same order of precedence that you're familiar with from your algebra classes. So multiplication is going to be evaluated before addition. So this expression, 3 plus 9 times 5, 9 times 5, will be evaluated first, which is 45. And so this expression simplifies to 3 plus 45. And then the addition operator can be evaluated, and 3 plus 45 is 48. So this entire expression, 3 plus 9 times 5, evaluates to 48. We can also always take the kinds of mathematical expressions that we're probably used to seeing formatted algebraically and render them in a linear form using just the mathematical operators of a programming language like Python or Java. And so here's an example. We have this algebraic expression with this whole top half here being divided by this bottom half here. And we can express that in a linear form, a textual form, by placing all the elements of the top half inside a set of parens, dividing by the bottom half, which is inside of a set of parens. The bottom half, in this case, algebraically 4a, we would just express that as 4 times a using the asterisk, which is the multiplication operator. Negative x, we can use the negation operator on x, plus z squared, we can use the exponentiation operator, z star star 2, and so on. And it's always possible to convert or represent any algebraic expression in this form using the operators of a programming language. The basic operator set: addition, subtraction, multiplication, division, and modulus, which is also called the remainder operator. A lot of learners forget about the remainder, but this is actually probably how you learned to do division back in 3rd grade, when you would divide 7 by 3, and you would get an answer that's like 2 with a remainder of 1, because 3 goes into 7 twice, and that's 6, and that leaves 1 left over. And so there's just an operator built into the programming language for still doing that kind of operation. It's surprising how often that comes in very handy when we're writing programs. So let's talk about relational operators. They're very similar in some ways and different in some important ways to the mathematical operators. In this case, we use them to compare values. And we can compare just about any kind of values as long as we're comparing values of the same type. So integer to an integer, or a float to a float, or a string to a string. And when we compare two values with the relational operators, we're going to get a Boolean output. So with the greater than operator, we're going to get a true output if the left-hand value is indeed greater than the right-hand value, and so on. We've seen some examples of expressions that we can evaluate. 5 greater than 3, well, that's true, so that would evaluate to true. 3 less than 5, that's also true. 5 is less than 3, that's not true. And so these evaluate to true or false based on your intuitive sense of how they should evaluate. 3 is less than or equal to 5, that's true. 5 is greater than or equal to 5, that's true. 5 is greater than or equal to 7, that's false. 5 is equal to 5, that's true. 3 is not equal to 5, that's true. 3 is not equal to 3, that's false. And so anytime you have an expression that has a relational operator in it, the result of that expression will always either be true or false. If it's not true, you can be guaranteed that it's false. Here's a couple of other examples. We can compare Boolean values. So we can compare the value true to the value false using the inequality operator. So this is true is not equal to false, which is of course true. And that may seem a little strange, but it does make sense. And then here we have two mathematical expressions on either side of a relational operator. And in this case, the mathematical expressions will be evaluated before the relational operator. So what we have here is 3 plus 5 times 2. 5 times 2 will be evaluated before the 3 is added. So 5 times 2 is 10, plus 3 is 13. So we have a value of 13 on the left-hand side of the equality operator. On the right-hand side, we have 7 times 2, which is 14, minus 1, which is 13. So we also have 13 on the right-hand side. So we're comparing 13 to 13, and they're equal. So that's true. Here we have 1 minus a negative 1. So that's 2. And then on the other side, we have 2 times a negative 1, which is negative 2. And so this says 2 is not equal to negative 2. And that, of course, is also true. We can also use these relational expressions as the right-hand side of an assignment statement. So we can store the value of the expression. So we have this expression here, age is less than or equal to 16, and we're going to store the result of that in a variable called young. And of course, we would end up storing true in the variable young if the value stored in age was less than or equal to 16. Otherwise, we would store a false there. Here's another expression, age greater than 65, and we're assigning the result of that to old. And so this is a way for us to generate true or false values based on some expression. Balance is less than or equal to 0, storing the result in a variable called broke, or balance greater than 1,000, storing the result in a variable called rich. Here's one that might seem a little strange as you read it. You are out equals strikes equal 3. So if the value stored in strikes is exactly equal to 3, then we would store a true in you are out. Otherwise, we would store a false in you are out. Now, a couple of caveats when you're dealing with relational operators, especially when you're comparing floating point values. Always remember that floating point values are prone to rounding errors. So we can often not store an exact representation of many floating point values in a floating point variable. Here's an example where that could come out different than you might expect. So here we're storing 2.0 in a variable a, and then I'm using the exponentiation operator with an exponent of 0.5, which is equivalent to getting the square root of a, storing that in b, and then I multiply b by itself to square it again, and you would intuitively think that we would end up with a 2.0 in c, but in fact we don't. And that's because when we take the square root of 2, there's no exact representation for that in floating point values. And so the value that gets stored in b is not quite the square root of 2. Therefore, when we square it, we don't quite get 2. Therefore, those values are not equal. So when you're doing comparisons with floating point values, you probably don't want to do comparisons for exact equality. You'd probably want to take the absolute value of the difference between the values that you're comparing. And if the difference is very, very small, then you could consider them to be equal. The relational operators also work on string values, so we could compare strings containing, say, Alice or Bob or Alex. And so in this case down here, I'm comparing Alice and Alex for equality. And of course, those strings are not equivalent, so we would end up storing a false at x. And here we're saying Alice is not equal to Alex. And that, of course, would be true. And then here we're checking Bob is greater than Alex. And so what does that mean to say that one string is greater than another? Again, this is going to actually work in a way that's fairly intuitive to you. If you were to alphabetize a list of names, you would probably place all the names starting with an A before all the names that start with a B. And so the larger ones coming later, so Alex would be less than Bob, and Alice would be less than Bob, and Alex would be less than Alice. So in this case, we're comparing Bob and Alex, and Bob is indeed greater than Alex because the B is greater than the A. And then down here we have a comparison of Alex to Alice. And in this case, they both start with an A. The second letter is both an L, but they differ on the third letter, and the E comes before the I, so it's not greater than. And so it's always going to evaluate the relative values of strings in the way that you would organize them alphabetically. Under the hood, the reason for this, if you'll remember, is that these textual representations of these characters are actually encoded as binary numbers. And the true fact is that a capital A is represented by a binary number that's smaller than a capital B.